Is Earth's biggest megaquake here? Here are 3 signs that could link to one event. We're counting down the 7 key triggers scientists are urgently watching, each one a possible domino in a chain reaction. From strange, silent tremors deep beneath the Pacific Northwest, to mysterious seafloor clues and tectonic knots that could connect entire fault systems, these warning signs reveal how a megaquake could go far beyond anything in recorded history. Some are hidden signals you'll never feel. Others are sudden shifts that could set off catastrophic cascades affecting millions. But which fault line could really unleash Earth's largest linked quake? Let's begin at the quietest threshold with number 7. The deep, secret pulses now rippling under the surface. Number 7. Deep within the crust beneath the Pacific Northwest, a silent phenomenon begins to stir. Known as episodic tremor and slip, or ETS, these slow, deep quakes repeat every 13 to 16 months, moving unnoticed beneath cities from Vancouver to Portland. Unlike the jolting shock of a classic earthquake, ETS releases energy gradually, equivalent to a magnitude 6 or 7 event, over weeks, not seconds. GPS time series and dense seismic arrays reveal these pulses as subtle shifts, sometimes just millimeters, quietly reloading stress along the region's largest faults. The most recent full-margin ETS episode ended just 11 months ago, shortening the interval before the next stress release. While most people never feel these tremors, scientists track them as early signals, a faint drumbeat that can modulate the timing and size of future megaquakes. The question remains, will these invisible pulses act as a pressure valve, or are they setting the stage for something far more violent just beneath our feet? Number 6. Pythia's oasis emerges as a silent anomaly on the seafloor off Oregon, a serene stream of bubbles rising from the dark. Yet the implications reach deep into the heart of the Cascadia megathrust. Here, remotely operated vehicles recorded fluid temperatures nearly 9 degrees Celsius above the icy ambient waters, and heat flow measurements surged to 9 times the regional background. Chemical signatures trace these fluids to origins nearly 4 kilometers beneath the seafloor, within the fault zone itself. This is not just a gentle seep, but a pressurized vent where water escapes under near lithostatic pressure, carrying the fingerprint of the Earth's buried stresses. Such overpressured fluids act as natural lubricants, reducing friction and weakening the very plane where tectonic plates grind past one another. In this tranquil oasis, scientists see a possible mechanism for catastrophe. If fluid pathways like this extend along the fault, they may create hidden weak zones, allowing ruptures to jump farther, faster, and with less resistance. The question now lingers. How many more such gateways lie unseen, quietly priming the fault for a rupture that could span the entire margin? Number 5. Deep beneath the waves off Northern California and Oregon, the ocean floor preserves a silent archive of catastrophe. Within the layered muds of Noyo Canyon and the submarine canyons of Cascadia, geologists have discovered paired sediment beds, turbidite doublets, that may serve as the geological black box recorder for ancient megaquakes. Each doublet is a striking sequence, a fine-grained layer overlain by coarser sand, sometimes with an abrupt erosional contact, deposited in rapid succession. These features suggest not just a single earthquake, but 2 immense shocks striking close together in time, potentially a Cascadia megathrust event, followed by a rupture on the northern San Andreas Fault. In Noyo Canyon's 49 PC core, 31 Holocene turbidites are stacked through the last 10,000 years, with more than half of the major events forming these distinctive doublets. Bayesian radiocarbon dating, applied to foraminifera and plant fragments nestled above and below each turbidite, narrows their ages to within 80 to 150 years, close enough that, within the margin of error, 2 quakes could have occurred within decades, or even less. Across multiple canyons, more than 50% of these doublet events align, a pattern difficult to explain by storms or floods alone. The lack of intervening hemipelagic mud and the grain size reversals reinforce the case for near-synchronous fault ruptures. Yet, the evidence is not without controversy. Erosional scours can blur boundaries, bioturbation can mix microfossils, and confound dating. Still, as Dr. Chris Goldfinger of Oregon State University notes, the evidence from turbidite sequences suggests that these faults have ruptured together in the past, which raises the possibility of a future multi-fault event. For now, these doublets remain a forensic clue, persuasive but debated, leaving open the question of whether the next megaquake will echo the linked disasters hidden in the canyon's ancient mud. Number 4. The invisible hand behind earthquake dominoes. Stress transfer mechanics. When one fault slips, it doesn't just relieve local strain, it sends out a shockwave of stress, redistributing invisible loads throughout the crust. Scientists call this Coulomb failure stress change, or delta CFF, a measure of how the shifting Earth makes nearby faults more or less likely to break. Even a modest increase of 1 bar about the pressure of a car tire can double the odds that a neighboring fault will rupture within years or even days. Numerical models, built on decades of seismic records and geodetic inversions, reveal that these stress lobes often reach out 30 kilometers or more from the original rupture, painting the landscape with zones of heightened danger. In the aftermath of Chile's 2010 Mal earthquake, aftershocks clustered precisely where delta CFF peaked, confirming that stress transfer is no abstract theory, but a real, measurable force. These color-coded lobes, mapped in vivid reds and blues, show where the Earth is primed for its next slip, and where it may hold fast. For the West Coast, this mechanism is more than academic. The geometry of Cascadia, the northern San Andreas, and the Mendocino transform means that a massive rupture on one could load the others, triggering a cascade of failures. Unlike isolated earthquakes, this is a system where faults can talk, one slip setting off another, like a line of dominoes toppling in sequence. As researchers refine their models, the possibility of a linked megaquake becomes not just a nightmare scenario, but a calculable risk. The stage is set. The question is whether the next big shock will stop at one fault or leap across boundaries, unleashing something far larger than history has yet recorded. Number 3. The northern San Andreas Fault slices through California's coastal ranges, a scar in the earth that runs from the Mendocino Triple Junction southward, threading its way past towns, highways, and the heart of the San Francisco Bay Area. This is no hidden menace. Here, the boundary between the Pacific and North American plates is written into the landscape: offset fences, cracked roads, and the jagged trace of the fault itself. The San Andreas is a strike-slip fault, meaning the ground on either side grinds horizontally, storing energy that can be unleashed in a moment's violence. Its 1,200-kilometer length is among the longest onshore faults in North America, accommodating the relentless northwest march of the Pacific Plate. The memory of 1906 endures, a magnitude 7.9 earthquake that snapped water mains, ignited fires, and left more than 3,000 dead in San Francisco. Along the fault, the ground lurched sideways by over 6 meters in places, a shift so abrupt that entire orchards and railways were offset overnight. More recently, the 1989 Loma Prieta earthquake, magnitude 6.9, struck during the World Series, collapsing freeways and bridges, killing 63 and injuring thousands. Today, more than 7 million people live within 25 kilometers of the fault's northern segment. Critical infrastructure, water, power, transit, crosses its path at dozens of points, creating a web of vulnerability that is mapped and remapped by emergency planners each year. Paleoseismic trench studies reveal a pattern of surface rupturing earthquakes recurring every 150 to 200 years, with evidence of violent ground shaking extending back millennia. Lifeline studies warn that a major rupture could sever power and water for weeks, isolating neighborhoods and overwhelming hospitals. First responders, like Petaluma Fire Chief Susie Byers, voice a sobering reality. Evacuation routes may be blocked by collapsed overpasses or fires. In some scenarios, help simply won't arrive for days. Unlike offshore faults, the San Andreas runs beneath dense urban corridors, magnifying the human cost of any triggered event. If stress from a neighboring rupture, transmitted through the crust in a matter of minutes or hours, were to load this fault, the result could be catastrophic. Bridges could fall, gas lines ignite, and entire communities face cascading emergencies. The northern San Andreas stands as the likely recipient of transferred stress, a fault primed for motion, waiting for the right nudge. With each passing year, the tension grows, and the possibility of a linked megaquake moves from theory to a pressing concern for millions living atop this restless boundary. Number 2. The Cascadia Subduction Zone stretches for nearly 1,000 kilometers off the Pacific Northwest, a sleeping titan whose silence belies its catastrophic potential. Here, the Juan de Fuca plate grinds beneath North America, locked tight in a tectonic embrace that has lasted for centuries. Along this margin, the fault is capable of producing earthquakes larger than magnitude 9, events that can hurl 30-meter walls of water onto coastal towns and erase entire landscapes in a single night. The last time Cascadia broke its silence was on a winter night in 1700. In Japan, villagers recorded an orphan tsunami that struck without warning, the wave's arrival unlinked to any local shaking. Only centuries later did scientists, sifting through Japanese temple records and the ghostly outlines of drowned forests in Washington and Oregon, piece together the story. A magnitude 9 quake had ripped through the Cascadia megathrust, sending a tsunami racing across the Pacific. As paleoseismologist Dr. Chris Goldfinger explains, the evidence from stratigraphy and oral histories is overwhelming. A full margin rupture occurred, and it was felt around the world. Coastal stratigraphy tells the same story. At Cannon Beach, tsunami run-up models show waves reaching over 8 meters, while buried soils and sudden drops in land level, subsidences, are preserved in the mud. Layers of sand, carried far inland, mark the violence of the ocean's incursion. Over the past 10,000 years, scientists have counted at least 43 full-margin Cascadia events, each leaving its mark in the sediment and reshaping the coast. Yet, in the centuries since 1700, the zone has been eerily quiet. Modern instruments register only faint tremors and deep, slow-slip events, but the locked portion of the fault continues to accumulate strain. The probability is sobering. There is a 37% chance of a magnitude 7.1 or greater earthquake on Cascadia in the next 50 years, according to recent hazard models. NOAA simulations warn that in a repeat of 1700, tsunami waves could reach the shore in less than 20 minutes, leaving little time for evacuation. The quiet beaches and tranquil forests of the Pacific Northwest mask a sleeping threat, one that could awaken with little warning. Yet, the Cascadia Subduction Zone does not exist in isolation. Its southern end approaches the Mendocino Triple Junction, a structural bridge where the energy of a megathrust rupture could, in theory, leap southward, loading neighboring faults and setting off a cascade of destruction. The question that haunts seismologists is not just when Cascadia will break, but whether its rupture will remain contained or trigger a chain reaction that could redefine the meaning of a megaquake for generations to come. And finally, in first place, the Mendocino Blanco Transform Faults and the Mendocino Triple Junction, a tectonic crossroads where the fate of 3 great faults may be decided in a single, world-shaking instant. Here, off the rugged coast of Northern California, the Pacific Plate, North American Plate, and Gorda Plate converge in a mechanical knot that is anything but simple. The geometry is startling. To the north, the Cascadia Subduction Zone dives beneath the continent, storing centuries of strain. To the south, the northern San Andreas Fault grinds through the coastal ranges. And between them, the Mendocino and Blanco transforms slice laterally through the crust, each boundary poised to transfer stress, each one a potential bridge for rupture. Seismic cross-sections from the 1993 Mendocino triple junction seismic experiment reveal the Gorda slab's edge plunging at least 150 kilometers inland, its presence marked by a sudden break in crustal reflectors, a tectonic fault line in the very architecture of the Earth. Wide-angle data trace these abrupt transitions, aligning with the deep roots of the Macama and Bartlett Springs faults, which cut through the entire crust and emerge as possible highways for stress transfer. Beneath the surface, a 12-kilometer thick layer of fluid-rich lower crust stretches south of the slab edge, imaged by ocean-bottom seismometers and tomography. These fluid zones, detected up to 60 kilometers south of the slab's terminus, create regions where the rocks are weakened, prime territory for a rupture to jump boundaries that would otherwise act as barriers. The Mendocino Triple Junction is not just a static puzzle. In late 2021, the region was rocked by a complex, triggered sequence of earthquakes, a swarm that, while confined to the offshore transforms, sent a ripple of concern through the scientific community. The lead investigator of the MTJ seismic experiment described the area as a mechanical switchboard, where the right combination of forces could send a rupture cascading from subduction to transform and onward to strike slip. The southern edge of the Gorda slab, fragmented and riddled with microseismicity, stands as both a gateway and a gauntlet, a place where the brittle crust of the subduction zone gives way to the ductile, fluid-saturated rocks of the transform regime. Recent tomography highlights the slab window's migration, where upwelling asthenosphere and tectonic thickening create ever-shifting boundaries. This conveyor of crustal fragments and partial melt may act as both fuse and firewall, dictating whether a megaquake can traverse from Cascadia to the San Andreas. Deep reflector breaks align with major faults, suggesting that the mechanical continuity necessary for a through-going rupture exists here, and nowhere else on the West Coast. The evidence is mounting. Abrupt reflector breaks, deep-cutting faults, and fluid-rich weak zones all converge at the Mendocino Triple Junction. It is the only place where a rupture could, in theory, leap from one tectonic regime to another, bridging the subduction zone, the transforms, and the strike-slip fault in a single, monstrous event. As seismicity continues to cluster and the crust grows ever more fragmented, the question is not if these boundaries will interact, but when. At the Mendocino Triple Junction, the world's most dangerous tectonic experiment is quietly underway. For scientists and the millions living above these restless plates, it's only a matter of time. From silent, slow-slip tremors deep beneath the Pacific Northwest to the high-stakes Mendocino Triple Junction at the top of the list, these 7 entries reveal just how interconnected and unpredictable Earth's biggest megaquake could be. What's most shocking is not just the magnitude each fault can unleash alone, but the emerging evidence, from paired turbidite layers to real-time stress transfer models, that a single event could jump between faults, multiplying destruction. Across all entries, a common thread emerges: hidden connections, be it through fluid-lubricated fault zones, invisible tremor cycles, or the linchpin triple junction, can turn isolated risks into a cascading disaster. The ranking highlights why the Mendocino Blanco transforms stand at number 1. Only here does the physical bridge exist for a true multi-fault rupture. Ultimately, this list shows that the line between routine seismic activity and a once-in-history megaquake is thinner than we imagined. Understanding these links isn't just science, it's a matter of survival for millions living above these restless boundaries.